Okay, it's now time to start with the chapter 8 in Griffiths, and that concerns conservation laws. As you can think of currents being involved in this, local charges, the time change of local charges is carried by currents, etc. So what's the best representative that we have for this? It's really the continuity equation. So let's say that we have a certain volume V, and the charge that we have in there is just going to be some Q inside this volume V as a function of time, integral over this volume, d tau, of the charge density at a certain space-time point, like this. Okay, and so we know how to talk about conservation of charge in this, because what we say is that the time derivative of the charge in this volume is really minus the integral over the surface bounding this volume of the current going through dotted into the surface element. Okay, so really this side here can be just written as the integral over the volume of the charge density like this, differentiated with time. So I'm just telling you stuff that you know very, very well. This side here you can rewrite with the divergence theorem into an integral over the volume of the divergence of the current. And lo and behold, we get the continuity equation for charge, that the time derivative of the density plus the divergence of the current vanishes. Okay, really this is a direct consequence of Maxwell's equations. You can just derive this identity from Maxwell's equations directly. That's essentially what we just did. Okay. One thing to note is that the form of a continuity equation like this is not limited to just talking about electrical charge. Any conserved quantity that you can think of, any quantity that has a global conserved quantity, so some value that changes, that does not change in time, any object like that will have the equivalent of a continuity equation. It's related to Noether's theorem, essentially. You've got the local charge, the local current associated to that charge. So these two are kind of dual to one another. They're related to one another through the continuity equation. We'll see more examples of that in the coming minutes. Okay, now you see, we're talking here about like particle number conservation. Charge conservation is really conservation of particle number modulated by the sign of the charge that it carries. But we can think of other things that are conserved. So of course there's energy. So if energy is stored in electromagnetic fields, then there has to be a flow of energy. Energy can be pumped in them. The fields can give energy. So we should be able to write the equivalent of a conservation law, of a continuity equation for energy. So let's see how that would work. We already know that the energy in electromagnetic fields can be stored either in the electric fields or in the magnetic fields, and we've seen the form that this takes. Essentially, we've got the electric field contribution, which is just the integral over space of the square of the electrical field, and in the magnetic case, it's a very similar expression, 1 over 2 mu 0 integral over space of field squared. Okay, we'll get back to this expression here because that gives us some global quantity, the total energy, which should somehow obey some conservation law. Right, now the thing we're going to do is really do a derivation from scratch. How are we going to do this? We're going to assume that there are some fields E and B that work on some charge and current distributions. So let E and B work on charge distribution rho and current distribution J. So what is the work done? Well, the work done would be the integral of the force times the displacement. So let's just consider a little infinitesimal contribution to this. So when we look at the Lorentz force law, so we'd have F dotted into dl. What's the force? Well, the force would be for a certain charge. It would be Q times E plus V cross B. Okay. With the displacement, you see, the displacement would be some speed V times some delta t. Say we compute the work done in a certain differential time element. But this simplifies, right? Because you see, the V cross B has no component in the direction of V. So this whole thing just becomes QE dotted into V times dt. Right. So in the continuum, where we're not looking at discrete charges, but we're looking at distributions of charges, this simply generalizes to so in volume d tau, I would have a charge rho d tau moving at velocity v such that the current would be just rho times v, right? Current is essentially charge density times the velocity at which these things are moving. In that case, I can write the following thing. So the differential amount of work that's done per unit time is going to be the integral over my volume of E dotted into the current density, right? Just comes directly from the generalization of this to the more continuum configuration we're looking at. Okay, so this integrand here, E dotted into J, is really the work done per unit time per unit volume. Yeah? So if you want, it's the power that's delivered per unit volume into my system. Okay. Now we can rewrite this with Ampère-Maxwell. So using Ampère-Maxwell, what we can write is that E dot J, I just substitute for J from Ampère-Maxwell. So what does that give me? I have a 1 over mu 0. And then I've got an E dotted into the curl of B. And then I have to subtract the other term, which has, you remember, the minus mu 0, epsilon 0, but now I'm dividing by the mu 0 because of Ampère-Maxwell, so I've got an epsilon 0 left. And now E, this one here, E, dotted into the time derivative of E. Okay, so so now we can do a few simplifications here. So we have a handy rule that's in the book, product rule number 6. It's about the divergence of cross product between two fields. So let's just write it. I've got divergence of E cross B. That's going to be B dotted into curl of E. And then just the converse, E dotted into the curl of B. Okay, so that's one thing. Now, so Faraday tells us that the curl of E that I have here is just equal to minus dB dt. Okay, so that's one of them. So what I get when I look at my whole thing is that I can write, so I can bring this on the side and then bring this on the other side. So I can write that E dotted into the curl of B, yeah, which I'll want to substitute here. That this thing here is just minus B dotted into dB dt, okay, minus the divergence of E cross B. Okay? Now a couple of things. So this thing here, so the B dotted into dB dt, it's just 1/2 times the time derivative of B squared. And the same thing holds for E here. Yeah, so this thing is just 1/2 d dt of E squared. Okay? So putting things together, right? I go back here, so this E dot J, field dotted into current density that I have here, I substitute for this here. You see I've got two handy things. I've got the derivative with time of essentially like E squared plus B squared, modulo the epsilon 0 and mu 0. Okay, so I've got the minus 1/2 d dt of epsilon 0 E squared plus 1 over mu 0 B squared. Okay, and now the last term that I have is just this one here that I get from here, so we shouldn't forget the 1 over mu 0. So I get 1 over mu 0 with the divergence of E cross B. Right. So that's all very swell. Now I've got a handy expression for E dot J that I want to substitute back into this expression here for the work done per unit time. Okay. So putting everything together, we get a really important result that is called Poynting's theorem. Poynting. Okay, so what's Poynting's theorem? Differential amount of work is equal to minus time derivative of the integral over your whole volume of a quantity 1/2 epsilon 0 E squared plus 1 over mu 0 B squared. Okay, this quantity is just interpreted as the density of energy inside the electromagnetic fields. And now just doing the integral over the volume here and using the divergence theorem, I just get minus 1 over mu 0 integral over the bounding surface of the volume I'm considering of the surface element dotted into E cross B. Okay, so kind of looking good because the first term here is really the time derivative of the total energy in the electromagnetic field, and somehow this term here represents the rate at which the energy is carried out of my volume by the electromagnetic fields. Okay, so that's like a nice little interpretation. We can make this even cleaner by just defining some objects. So we can define the Poynting vector. Always love that name, yeah, the Poynting vector. It's pointing somewhere, and it has a very important physical interpretation. So the Poynting vector S is by definition just this simple combination that we're using here, 1 over mu 0 E cross B. Okay? So Poynting's theorem then becomes really quite compact. We just say that the rate of work is equal to minus d dt of the total electromagnetic energy minus the integral over the bounding surface of the Poynting vector. Okay? Where the total electromagnetic energy is just what we've written above, right? So integral d tau of epsilon 0 e squared plus 1 over mu 0 b squared. Okay? Right. So you see, we can define. Well, maybe I'll just define it this way. Yeah. So I'll just say that this is integral d tau of little u e m, where little u e m is just the 1/2 times this this combination here. It's just the local electromagnetic energy density per unit volume that I have in my system. Okay, so just one little step further. My form that I have here. So let's say that essentially. So say that. Say that there is no external work. Okay, so there are no external forces in there. So the thing that has to occur is that the total of this thing has to be equal to 0 because there's no external influence onto this. So that means that I should get that the the time derivative of the integral d tau of u e m. So I'm just writing the right-hand side here explicitly, plus, I can again undo the divergence theorem here, again do the integral over the volume, but now of the divergence of S, okay, over a certain volume here, and then since V is arbitrary, what I just get is that the time derivative of the electromagnetic energy plus the divergence of the Poynting vector is equal to 0. And you see that's the, again, so it's again the Poynting theorem, but now in differential form. Okay, and look at the form of the equation. Of course, it is just precisely the same mathematical form as the continuity equation, except that now we're not talking about charge conservation, we're talking about energy conservation. So the change in the energy density has to be carried by some current. So the Poynting vector really represents the energy current in your theory. Okay, very same kind of equation as the continuity equation for charge that we have started here. Okay, precisely the same thing. Now, fine, carry on. Name me other things that are conserved. Well, there's momentum, there's angular momentum, and we'll see that in the coming little lecture. maybe before I do that, actually, I should just do, for example, the little case that's given in Griffiths 8.1, just to illustrate what that is. So it's about current in a wire. And what's the setup? So you would have a certain wire, okay, and there's a current flowing in the x direction like this. So it's as if, so I mean, if you want, you put the so there's a length L here. There's a voltage difference V between the two ends. So the electric field is V divided by L in the x direction. And of course, what you'll remember from our earlier things is that there will be then a current going through the wire here. The magnetic field is going to be circumferential around this. Okay, there's a current intensity I going in this, so the magnetic field is going to be mu 0 I over 2 pi times a being the kind of distance, this, so the radius a, if you want, like this. Okay, and now what we're going to do, so B, the question is to compute the Poynting vector at the surface. Okay, so the B is 1 over the distance, but now because we're at the surface, I put the A here. Okay, and this goes like this. So therefore, my S is 1 over mu 0 E cross B. So what is that? Well, that's going to be 1 over mu 0 times mu 0 I, so that goes V times I, okay, over 2 pi L times A. And then the x hat dotted into the phi hat, but this one here is just minus the radial vector, so in cylindrical coordinates, where I put the axis of the cylinder along x like this. So my Poynting vector is equal to minus v times I divided by 2 pi AL with the S radial unit vector. Okay, so the energy per unit time, energy per unit time passing through the surface okay, passing through the surface of the wire. So what's that going to be? I will want to integrate over the surface the dot between my normal surface element and the Poynting vector. And because of the symmetry of the problem, this is just the size of S, so this number here, times the surface that I'm considering, which is 2 pi A times L, okay? And if I look at what that is, so this is just minus V times I, okay? So essentially, you'll recognize this formula just as the Joule heating. Okay, so the normal here is an outward normal, so the minus sign means that the wire is heating up with a power which is given by the product of voltage times the current. Okay, and this is what you expect from what you already know about wires. Okay, so that just shows you how to use Poynting's vector to compute energy flow in these systems.